just so we can see these stack frames, I definitely think it's important that if you see some snippet of assembly like this, you can manually walk through and create and destroy the stack frames by yourself. So I'm just going to show this quick. Over to the board. Now this is a very simple example. It doesn't have local variables, for instance. So these stack frames are going to be quite simple. But we start out at main at address 401010. So that's where we're assuming this is the first address that it executes. The first instruction that executes, it does push EBP. And so we wrote this always as saved EBP. Right, so wherever EBP was when we got into this code, it takes that register and saves it on the stack. And when you save that on the stack, your stack pointer was wherever it was up here. But we know at this point, when that gets put on there, ESP points right here right now. Right, you push something on the stack, ESP is always pointing at whatever's on the top of the stack. So, and a refresher for people who didn't have this, I write my stack frames like this is the bottom, but this is high addresses. And this is the top, and this is low adders. Right? So I said stack grows towards low addresses, so our stack frame is going to grow this way. Other people write their stack frames vertical, growing up. Other people write them horizontal, going left or right. Whatever. Push EBP. Next instruction, move ESP. Remember, we're moving from right to left. Move whatever's in ESP into EBP. So right now, ESP points here. We want to change the EBP register so that it now, EBP has the same value in it as ESP. So they're now both pointing at the same place. They're both pointing at the same EBP. Next, we immediately move into calling a subroutine. Now we said the side effect of the call instruction is that it pushes the address of the next instruction after the call onto the stack. So the next instruction after the call is 401018, right? So that's going to get pushed onto the stack. So we're going to go 401018. That gets pushed on the stack. When it gets pushed onto the stack, ESP is consequently updated. Right? ESP now points there. And we have transferred to the code at sub, or subroutine, not subtract. All right, first thing it does is it issues our standard stack frame setup, push EBP, move ESP to EBP. All right, so whatever this was, we're just going to make up some number for it for having some concrete values. We're going to say it was 12FFD0 or something like that. It's going to take whatever was in EBP, and sorry, this is the address of that in memory, this location of stack in memory. It's going to take that, it's going to save that. So this is a new saved EBP, and it's specifically 12FFD0. And this is some, real number as well. It's whatever was way up there. We don't know what that is out of our stack frame. We do that, and then I'm just going to say we right away move the ESP to EBP. So ESP was pointing here when we did it. We're going to move EBP there as well. So when we pushed it, this pointed there. And when we did the next instruction, move ESP to EBP, that now points there. So now we're pointing here, and we said, like, these are always kind of like linked lists because EBP points at this one points back at this one points at that one up there. And so that's how that's when debuggers do commands like, print stack trace, print to show you what function you're currently in. They're walking this list, and then they're looking at this instruction pointer that they assume is going to be immediately before the stack frame, and they're saying, which function is that from? And then they say, you were in main right here. All right, so the only thing we just did the subs, move ESP to EBP, and then the only thing it does is move hex B to EAX. All right, anyone remember why it's moving it to EAX based on that C code? Yes? Yep. Per convention on x86, EAX is the register used to store your return values. So in the C code, we see we're doing return hex beef. And so in the assembly code, we move hex beef to EAX so that when we return, if the function above us, the function that called us wants to check the return value, it knows to always check EAX. All right, so we did that, whatever. That has no effect on our stack. Now we get to the next instruction, pop EBP. We're starting to tear down the stack. We're doing pop EBP and return. All right, so the first thing, pop EBP says take whatever's on the top of the stack. ESP is currently pointing here. Take that and copy that value into EBP. All right, so we're popping it off the stack. So ESP is getting updated to point, updated to point here. And then EBP just got its value overwritten with whatever was on the stack, which happens to be 12FFD0. So EBP now points there. And then finally, we issue the return instruction. Right? That says whatever ESP is pointing to currently. I'm going to take that off the stack and put that into EIP. Right? We said EIP, you can't just like manually do a move instruction on. The only way to change EIP is to do calls, returns, jumps, that sort of thing. All right, so pop, or return rather. Return takes whatever's in ESP, which is right there, pops it off of the stack. So for a pop, ESP gets updated, and then that gets set into EIP. So that was 401018. We're now back to over to the slides. Bill over. He's doing other classes as well, so I shouldn't move around so much. Right, so when we do this return instruction, it takes whatever's on the top of the stack, which was this specific address, and it sets EIP to that. So we know immediately after that return instruction, we're going to be at this move hex foo to EAX. All right, back over to the slides. Wait, hold on, did Mike have something? That was the previous question. All right, so finally, we're back in main. We move hex foo to EAX, showing the pointlessness of moving hex beef there. And then finally, we're tearing down this stack frame as well. And we're doing, so I guess in other things, I'd called this like address of guy who called main or something like that. Address of instruction after call main. That was also on the stack at the time that we got into this thing, before we even pushed EBP, right? So we're at the pop EBP, so we take this right here, pop that off the stack. So ESP now points there. EBP points up here wherever the previous stack frame was. And then finally, return says whatever ESP is pointing to, pop that off the stack, and then go back to that address. And we said that address is the address of whatever code called main, because typically on Linux or Windows, there's going to be some C runtime initialization or something that occurs before you actually do the call to main. So in reality, when you start the thing up, it starts initializing your libraries, and then when everything's set up, it goes, call main. And so obviously, you can return from main back to that. All right. Any questions on that? Any questions on the setup or teardown of the stack? All right. On we go, 1 hour into the real stuff. This is what you're going to learn. I'm pretty sure on this picture, we cover everything except this XCR0, which I don't know what that is even. And, yep, I'm pretty sure we cover everything except that one thing. So, by the end of this, you'll know that. Isn't that nice? Yes. Pause for effect. Can someone please say this is madness? Yes.
This is madness.
This is X80! No, intermediate X86! Right, and as a nerd, you shouldn't accept this ridiculousness, because you definitely didn't say it at this point, right? That's obviously during the end of the battle, but the messenger actually said it much earlier, but I couldn't find any pictures of him shouting at the messenger that were big and high quality and stuff. So that was a Google Images fail. And also I'm lazy and I didn't want to go out and get a screenshot from the thing. All right, so this is actually supposed to be your morning warm-up. This is just going to introduce you to a new instruction which has some utility. So I hope someday, these classes actually, get used by other people, and then they have like a remix video of me like shouting. All right. So CPU ID is CPU feature identification. So this is an instruction which tells you what features your CPU currently supports. Because as time goes on, they keep adding more features. And so if you want your code to be, you need your code to not just assume that something's going to be there, right? So when you have code which is meant to run across many things and be backwards compatible, etc., you need to check before you try to use some features like hyper-threading, or whether you even know you can go, whether it's 64-bit or anything like that. Especially hardware virtualization, right? It should be a quick and easy check if you write a hypervisor to not try to start your hypervisor using the hardware support for virtualization. If you just check and see it's not there, then you got to either use software-based virtualization or whatever. All right, so CPU ID instruction doesn't have operands like some other things like add and move, etc. In that sense, it doesn't have operands in the sense that when you actually call the instruction, you'll see any operands to it. It implicitly is always taking whatever's in EAX and doing something based on that. So you set up EAX before you issue CPU ID, and then based on whatever's in EAX, it's going to look up different information for you. And when it looks up that information, then it spits it out to EAX, EBX, ECX, EDX. So assume that before you issue CPU ID, you need to set EAX, and after you issue CPU ID, assume that A, B, C, D are all going to be overwritten new information. All right, and so there is a minor thing here which, ostensibly you shouldn't really ever have to worry about, but in reality, just to be, let's say you're running some software that you're going to run on early model 486s, you need to know whether you can even issue the CPU ID instruction. So it turns out that Intel added the ID flag to the eFlags register. And so you need to be able, so if your program can set or clear the ID flag, whatever the ID flag is right now, you need to be able to either, if it's 0, you got to set it to 1 and then go and check, did it actually get set to 1? If so, I can use CPU ID. If it's set to 0, you set it to 1, you wrote it back, and it's still set to 0, that means you may not use CPU ID. Same thing with 1. Is it older? So then this adds in the question of how do we actually read and write eFlags, right? So you have to actually set it. So previously we only heard of eFlags in the context of you do an add, and if the result is 0, the 0 flag gets set, right? All the arithmetic flags are in there, but or comparison flags or whatever you want, conditional code flags, we'll say. All of those are in there, but there's a whole bunch of other stuff in there as well. So for that, we need the push FD and pop FD instructions. So push FD is pushing the flags onto the stack, and specifically, we're using the D prefix here because to specify we want to push the D flags, or sorry, D word size D flags onto the stack, because like EAX and EBX and ECX, there used to be a 16-bit version back when Intel was only 16-bit called flags rather than eFlags. That was 16 bits. Turns out, although these all have the same opcodes, and we had talked a little bit in the last class about how you deal with ambiguity. Sorry, people on the thing, I was just pointing at all those C9Cs. Although these all have the same opcodes, Visual Studio will always force, if you type push F in some inline assembly, Visual Studio will always force a prefix on this opcode, which forces this to be the 16-bit version. So you'll get 16 bits rather than 32 bits. So by using the push FD, it's telling the assembler, hey, I really want this, 32-bit form, and then we'll give it to you. So
hey, Gino?
Yes, question. Go ahead.
Is all this information then just stored in microcode within the processor?
The information returned by CPU ID or the eFlags information?
The CPU ID information.
That's a good question. I don't know whether it's stored in microcode, but that would sort of make sense, but I would call it microdata. I don't know. I don't know to the extent that that sort of thing is stored as data, whether you consider that microcode or not. Unfortunately, I don't know enough about microcode to say one way or the other on that. It's certainly stored within the CPU, obviously, but where and how, I'm not sure. Good question, though. Should look into that. Yeah, and I always like questions where I don't know the answer, so I can go look into them later. So where is the CPU ID stuff stored? All right. So on so push just takes your 32-bit push FD takes your 32-bit E flags register, pushes it onto the stack just like anything else. Pop FD, same thing. It just says whatever's pointed to by ESP right now, take that, read it off the stack, stick it into the E flags register. There are a couple of flags that you actually can't set, which I think we'll get to late in the class. There's some flags which, for security purposes, you don't want ring 0 or ring 3 code being able to set. So later on, when we get to that, we'll talk about it. But most of the flags can be set just by pushing and popping. Yes.
So given that the difference between pop-F and pop-FD appears to be whether you get the uppers X, which bit is the ID flag?
Yeah, I should have put that into the slides. I keep like always thinking to put the CPU ID or the E flags into the slides, but you know, you're old enough now that you can handle the manual, so I will show you where the. So in the previous class, we said we only wanted you to think about there being a couple of E flags and everything else. I don't care. Let's find the E flags, shall we? All right, Q-12. Yeah, there's a there we go. All right. All right, so this is the E flags register. Where is it? One. Yep, there it is. All right, so so yeah, all that stuff that we talked about before, carry flag, parity flag, auxiliary flag, zero flag, sign flag, those are all your typical flags which get set. Those bottom, 8 bits, those are plus some reserved ones. Bottom 8 bits, only like 5 flags. Those are set for all your arithmetic operations and, in some other special cases as well. Trap flag we're going to learn about later. That has to do with debugging. Hold on one second. All right. Trap flag we're going to learn about later. Interrupt flag we're going to learn about later, and interrupts. IOPL we're going to learn about in input-output. That's just privilege level saying who is allowed to do input-output. Not going to learn about that. Not going to learn about that. No. I don't think we're going to learn about any of the rest, but IOPL, interrupt flag, and trap flag we're going to learn about later, and ID flag, as she asked, is bit 21 in E flags. So really what we're trying to do right now is dump this to the stack, do some bit masking to set, whatever. And so that's what I'm going to skip the actual code for this because it adds, unnecessary complexity, right? But we obviously, it says to set or clear the flag. So we need to go to the flag, check whether it's 0 or check whether it's 1, set it to the opposite, write it back, read it again, see if it got set to the opposite or not, and then if so, yes, we may use CPU ID. It's always going to succeed here, but you can go look at the code later, but it's really just, running through the combinations of if it's 0 now, do this, if it's 1 now, do that. All right. Yeah. All right, so back to CPU ID. Assuming we can set or clear the ID flag, we can use CPU ID. So what can we get out of that? All right, so in the simplest case, if you give EAX as 0, you set EAX to 0 immediately before you issue CPU ID. What you're going to get back out is first, EAX will now be a thing telling you the maximum input value for CPU ID information. That says, for what will look in the manual like this column initial EAX value, you'll come back with the value that says, hey, the maximum thing you may ask for on this CPU is you know, hex 12 or something like that, right? So then you look at the table and you say, okay, I can use all that stuff, but I can't use hex 13 and, because it's not anything that's on my CPU. And then also they have a little string in there, genuine Intel, which you can put together, and then you can print out, you know, hey, this is an Intel thing. And actually, again, this is something maybe I should put in. Maybe I'll just always go to Wikipedia on it. But so on other models, so you can tell, for instance, what brand of processor you're running, because other models will have these instead of genuine Intel, right? So AMD is better, authentic AMD, Transmeta CPU, rise.
The small one.
That's right, I like that. These are good.
The other vendors are very exuberant.
Yes. Well, you know, they're the upstarts, right? All right. So that's what you get back for genuine Intel. We'll run the CPU ID instruction in a lab here in a second. You'll see that you put it together. And yeah, I think I heard someone commenting, these things are out of order and stuff like that, right? So, well, maybe, no one did comment. And yeah, so it's, you have to put EBX, EDX, ECX for whatever reason. All right. And so there'll be some other stuff in the CPU ID. I think I'll show that in a second after we run the lab, but I'll show some of the other sort of information you can get out of it. All right, so this is our lab. Basically, the core of it is that, you know, you run this code, check if you can use CPU ID. If yes, then go ahead, run some assembly that says, you know, create a string to use the pointer EDI to store. Use EDI to store the address of vendor string pointer. And then we're going to put 0 in EAX, call CPU ID, and then we're going to take, you know, the EBX, ECX, EDX, and use those to put those chunks in the right order to print it out. Yes?
So, it's a little bit of a detour, but given that I hear all these things about the, you know, detect virtualization code relying on timing and so forth, do most virtualization systems actually duplicate some particular genuine processor CPU ID information?
In some cases, they'll just pass it right through. Interesting thing I noticed with my Fusion, VMware Fusion on my Mac, it reports my VM, my Windows VM, as an Core i7 or whatever, which is what my actual physical thing is, right? And on my Windows machines, it reports Core 2 Duo. Some may pass it directly through. In terms of the options that are available, for instance, the virtualization system may want to say, no, there's no such thing as hardware virtualization here. Don't be running any code which tries to, you know, turn that on, right? So it is going to be the case that some virtualization systems, you can think of it, hook calls to this instruction. I think it's actually just built into the, for instance, x86 hardware virtualization, but I don't know yet because I haven't been research that for the advanced class. But I've heard references in talks and stuff saying that, you know, they can hook, the hardware support for virtualization will allow the hypervisor to hook any call to CPU ID that happens inside the guest, and it can return whatever it wants at that point, right? So it can say this or that feature doesn't exist. Heck, I've even seen in like some of the VMware preferences, I don't remember what version, it'll say things like, yeah, export the NX bit or something like that. So we'll learn about NX later, but it's just the bit that's used for doing non-executable memory. And so the hypervisor will actually tell the guest VM, sorry, there's no such thing as this non-executable memory support. So yeah, they can hook that in some virtualization systems. Okay, so it went back to the point of detecting virtualization systems. There is some code. I tried to use it here, but it didn't seem to work because it always said that I was virtualized even when I was on physical. We can try it on these machines. Maybe we'll get a different result, but it just executes like a bunch of CPU ID instructions, for instance, and tries to see, is this CPU ID instruction going a bit slow, right? Is someone maybe intercepting it and returning whatever they want? So there's that. All right, so we're going to do the lab quick, just to have you walk through on your own and stuff a little bit. The first thing, do you all have the intermediate x86 folder on your desktop? Okay, hold on. There was a question before on the chat where Dave was asking, you know, whether a compiler would notice that the value returned from sub. So back in our example code where we had the, yeah, sorry Dave, since you don't have the mic, in the future tell Bill if, yeah, as he's doing now, but just tell Bill, you know, please interrupt Zeno. His question was, you know, in that previous stack example frame we saw, where like, you know, we moved hex beef into EAX, and then immediately after we returned, we just moved hex food. He said, you know, would the compiler notice that that's pointless and cut it out? Yes, absolutely. We always run unoptimized code examples in our things so that we have simple assembly which maps very one-to-one. If we run the optimized version of that example, it literally generates the instruction sequence move hex food to EAX return or something like that. Yeah, I don't think it even makes a stack frame. So, question as well?
Sorry, I'm going back to CPU ID, so that's a
Yeah, no.
So is a lot of those features I've noticed you can turn on and off from the BIOS.
Yep.
Is what CPU ID returns what's currently activated or what's possible, or am I deeply misunderstanding how this works? Because this is a little lower level than I usually
That's a
work.
good point. I don't know that. See, that's, I was kind of thinking when, I can't remember, you don't like to go by Willie, right? William, what is your preferred,
Willie's fine.
yeah, okay, I couldn't remember, yeah. So when Willie was asking before about the, you know, where is the CPU ID information stored in, right, is it stored in microcode or whatever, and you're saying, you know, there's this issue of turning on and off features in the BIOS and stuff like that. Again, I don't know enough yet in order to say concretely, but I was kind of thinking in that case that it seemed more to me like there would be some stuff hard-coded in the CPU, but other stuff is just going to be stored in some, you know, non-volatile stuff once you start up. For instance, maybe the NVRAM. But that's on my list of stuff to figure out. All right. So, all right, does everyone have, for people in the class or for people catching up, that's fine. This won't be, you know, a groundbreaking lab, so just get your remote people, get some lab environment set up, RDPing or whatever. People in class, do you have the intermediate x86 on your desktop? All right, open that up. Go to intermediate x86 code, and then open the intermediate x86.sla. That's the solution file. Visual Studio will open that. It'll have multiple projects within it. I don't know how your stuff is going to look compared to mine. Hold on a second. All right, so when you're in Visual Studio, you've got up your Solution Explorer somewhere. I like it over here. You expand CPU ID, expand source files, open up CPUID.c. And so this has all the set ID flag and all that stuff is, as we would expect, that's the complex stuff about checking whether you can set or clear the things. So the main thing is we're just going to go down to the very end of the code, set a breakpoint on return hex baseball. As a reminder, you set breakpoints by going over to the sidebar and clicking, and a little red bubble should appear, and that's setting a software breakpoint on that location in the code. Before we compile it, we have to set CPUID as the startup project. So right-click on CPUID actual project file, and then set a startup project. And then when you do that, it should appear as bold after that. All right, good, good. All right. So start a project, and then just go ahead and, you know, you've got your breakpoint, so go to debug and start debugging. All right, stop set hex, return hex baseball. And if you pull up the little command window and stuff, it's going to say max basic CPU ID, so that was the value returned in EAX, is hex D. So if we go to the manual, we know that on this system, we can look it through the table, and hex D is the maximum one we can actually issue on here and have it, you know, talk back to us. And then finally, we took that string and we rearranged the parts and we printed it out And so this says, yes, I am on a genuine Intel CPU. All right, so that's really all there is to this. Not particularly groundbreaking, but the point is, now you know how you can issue the CPU ID instruction. You just need to, most of the time you don't even need to check. If you're not expecting to run on early 486s, just go ahead and set, set EAX to 0 and then issue CPU ID. But then you need to know how to interpret the results, and the only way to do that is by looking at the Intel manual. Right? So, also in your intermediate x86 class, you've got a Intel Manuals 2008 and Intel Manuals 2009. Between 2008 and 2009, they changed some of the information about virtual memory paging and stuff like that, which we'll learn about in the second part. I like the original version because it has nice pictures and stuff that I use in this class more than the new version. The new version has what looks more like tables. So I prefer the Intel 2008 manuals. That's what all of your stuff in the slides is from the 2008 manuals, FYI. But right now we're looking for how do you interpret CPU ID results? How do you know everything you can find out? So in this volume 2A, ASM A through M, go ahead and double click on that, and then you can expand the instruction set reference and expand the A through M, and then just go find the CPU ID. And when you do this, this manual page is going to show you that table that I only showed you a part of before. And so now you can look down through the entirety of it, and you can see that, okay, let's go to hex D and see if there's even anything after that. Yep, so hex D is actually the last of the, quote, basic CPU ID information you can get. And when you get past the basic information, there's actually this extended information as well. So if you were to issue 80000, then you would get, now the new pointer which says, EAX will come back with your maximum value that's possible. Right? So you have to issue 0. If the only stuff you care about is in this initial part, 0 through D, then, you only need that. But if the stuff you care about, like, for instance, whether or not syscall sysret are available, then you need to call some of this extended stuff. And yes, we don't know what syscall and sysret are. This one, actually, this is the one I like. Processor brand string information. Very useful. And what it boils down to is in your Windows system information, for instance, this string right here, starting with Intel Core 2, blah, 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 ending in 3 gigahertz, all of that string is taken from the CPU ID information. So you can issue a CPU ID on a computer, and you can find out, it's an Intel Core 2 quad CPU. The model number is like Q9650, and it's running at 3 gigahertz, right? So that's definitely useful when you're trying to understand, what sort of machines are out there. I use that in my own work for identifying, is this machine the same as this machine, and therefore should I accept the same behavior from it. And let's see what else. Here's another thing which is interesting. Virtual and physical address sizes. Sorry, hold on. You're back. Virtual and physical address sizes is basically telling you, can the system only access 32 bits of memory? Can it access 36 bits of memory? Can it access 48 bits of memory? And so the virtual and physical has to do with, if you're actually in 64-bit mode, 64-bit mode doesn't actually, on current CPUs, doesn't actually have the ability to address 2 to the 64-bit bytes of memory. In reality, Intel constrains it for now, so it's something like 2 to the 48. I don't know, I was just skimming it. But point is, you can't even buy enough RAM right now to have 2 to the 48 worth of memory.
Sorry, Zeno.
Yep, go ahead.
Quick question.
Yep.
Somebody was asking what is the password for the VM. I didn't mark that down.
Oh yeah,
Sorry.
that is, well, we're not on the VM yet, so I'll tell you when we get there. No. It is awesome password for the win, and it is spelled as is currently on the board. Capital A on awesome, space, password, space, capital F, capital T, capital W, exclamation point. Awesome password for the win. All right. So yeah, anyways, back to that physical and virtual stuff. Yes, good point. Thank you. It basically is telling you right now how large of memory space you can actually address on your computer. Whether or not your OS actually allows you to access all of that, that's a different question. And actually what we found in the last class, which I should credit Roman D for, since I can't pronounce his last name, is we'd found that actually if you go to the Microsoft site, it turns out, even though we talk later on about the capability, even in 32-bit mode to access up to 2 to the 36 bits of memory, it turns out XP doesn't support that, but some of their other things like Windows Server 2008 and things like that will support that and beyond. But yeah, so this ends up being something where if you want to know how much actual physical memory the OS, has available to it, that will tell you this is how much RAM is actually installed in chips right now on my motherboard. And then let's see if there's anything else miscellaneous. There's a lot of little like, is this instruction enabled? Can I use generally speaking, can I use virtual machine extensions, stuff like that? Read is the TXT stuff in CPU ID?
Yeah, it comes out in ECX.
Do you remember for what input?
When EAX is set to 0. It may not be
That can't possibly be correct.
Well, it may not be in the 2008 manual.
But if EAX is set to 0,
No.
that's the genuine Intel. I don't think it'd be
They're
there.
obviously not on 0.
Is
Where's
the
it?
extended thing?
Is what?
Is the extended thing allow you to set?
Yeah, I mean, I would expect it to be somewhere in the extended stuff.
Yeah.
So maybe it's
What you
8.0.
actually ask for there is safe remote extensions.
Oh, yeah,
SMS.
that may not actually be in this manual, you're right, but
And that may be
okay,
in the later manual.
good point. All right, whatever then. Anyways, point is, as new features get added, when Intel's coming out and saying, hey, we've got AES in our chips now, and hey, we've got virtualization, you need to go find the latest Intel manual, pull up CPU ID, and that's how you'll find out whether or not your processor actually supports it. There we go. That is CPU ID warm-up for the day. Leave that back over there. Anyone have any other questions on CPU ID?
It's, you said EAX for 1, and it's in the 2009 manual.
All right. Well, so Reed says that TXT, Intel's trusted extensions technology. What is the
Trusted execution.
trusted execution
Trusted execution is technology.
technology?
And what you actually, it's like a several step process to find out if TXT exists. You have to first ask if safe remote extensions exist. And you can turn on the flag that allows you to ask if TXT is an instruction.
Right.
Let's say we have TXT.
Also completely disabled. I think it's like, I don't know any process that does one, not the other.
All right. So, final thing I would just say is that there's a good piece of code for Mac users. If you use the code here, he has a nice printout where he went through, enumerated, went and pulled in all the options, printed out nice little things telling you, here's your processor, here's it does or doesn't support this or that instruction. So the point is, there's probably other Windows things, but I never looked it up. But if you go search for like something, it'll show you CPU ID information. I'm sure there's something that already enumerates over all possible options and tells you all instructions and everything else. And also, if you really want to dig into it and write your own sort of thing, if you want to like get into this, there's actually a full extra little application note PDF that Intel has, which tells even more about CPU ID than the manual does. So now into CPU modes. So what we're going to do right now is we're going to search. So we're going to talk about where rings come from. When you hear ring 0, ring 3, kernel code, user space code, we're going to kind of shimmy our way towards figuring out where that all comes from. All right, so the first thing you need to know is that in the beginning there was real mode and it was suck. So real mode is when you restart your processor, it enters a CPU state called real mode. And basically, even now that we have more advanced machines, it starts up and it's essentially, think of it like a compatibility mode for their very first processors, because Intel is all about the backwards compatibility, and so they're always trying to make sure that you can keep using the old stuff when you've got the new stuff. So for instance, DOS ran in real mode, and it's a very simple thing. It doesn't have virtual memory, it doesn't have privilege rings, and it's 16-bit. So when you reboot, you're in 16-bit mode, and if you're running, some, well, I won't say that yet. So anyways, real mode is a very simple thing, 16-bit, and it doesn't have a lot of the features we're going to talk about in this class. So what most OSs actually run in is protected mode, and this adds capability to do multitasking, protected, blah, blah, blah. The things we care about for this class that it adds is the ability to do virtual memory, so paging and making it so that you can only have 256 megabytes of RAM actually installed, but it will allow you to access a 4 gigabyte virtual address space, right? And if you didn't have virtual memory, that would mean you could only ever access addresses within that first 256 megabytes, right? And so that's what it means to have virtual memory. It's saying I can access memory anywhere, but secretly behind the scenes, those virtual memory addresses get mapped to whatever physical addresses happen to be available. And that's going back to that CPU ID. When I said it's telling you your physical address space, if you only have 256 megs of RAM installed, it's going to tell you in that. It's going to say, look, you can only access 2 to the however many bits equals 2 to 56 megabytes. So one thing I'm pointing out here is just that in protected mode, there is a thing called virtual 8086 mode, but it's not, Intel doesn't actually really consider that a full processor mode. It's more like a backwards compatibility thing. So you're in protected mode and you've got the benefits of virtual memory and stuff like that. But let's say you want to run some old DOS programs in Windows 95 or Windows XP, something like that. What the OS or what the processor is doing is being put into virtual 8086 mode so that as far as those old DOS 16-bit programs are concerned, you're in 16-bit having all the memory that looks like old-style real mode. But in reality, you're still in 32-bit. It's just you've temporarily dropped down. But you don't want to drop all the way from real to protected, because then you'll be losing a bunch of the stuff when you try to go back to protected. You'll have to recreate it all. So it's just a way to kind of drop down a little bit to trick old programs for backwards compatibility. Yes?
Do you have any idea if that's sort of what Windows does when you ask it to run a program in compatibility mode for DOS?
I'm fairly certain that is, because there was that Tavis Ormandy, I think it was, I can't remember whether you called it a virtual 86 mode exploit or whether you just called it DOS compatibility mode exploit, but it definitely was exploiting the fact that there was some disparity between the expectations in terms of how the OS is looking at things versus how this old virtual 8086 was working. I'd wanted to add that in, but I've never gotten around to really understanding the full details. So unfortunately, I can't put it in, and it would also make, we already have too much material, and we can't get into virtual 8086 mode. So I just wanted to mention virtual 8086 mode or V8086 mode to say that it's there. It's sort of like a backwards compatibility thing, trick applications. It is what's used for things like compatibility mode in Windows, but it's not really technically considered a full mode, at least as far as the manual is. All right, so that's the main thing. Most OSs run in protected mode, but I said that when you reboot the computer, it starts in real mode. Therefore, that means there is some initial bootstrapping code which gets you out of real mode into a protected mode. System management mode, on the other hand, is something which became, was kind of neglected for a while and no one paid attention to it, but it became popular starting in 2006 when Louis, I don't know if I'm pronouncing his name right, but Louis Duflo wrote a paper on how you could bypass some of the OpenBSD kernel protections using system management mode. So OpenBSD, even if you're in the kernel, it's still trying to protect itself within that. But the issue is with system management mode, it turns out, so we said the kernel OSs are running in protected mode. System management mode is actually more, you can think of it as more privileged than protected mode in that when you drop down to system management mode, it's sort of like real mode in that, you know, it doesn't necessarily have paging unless, I think, what I've been getting from presentations that have been coming out is that you can still set up your own basic paging to use it, but so it can kind of access virtual memory, at least to the extent that it can access all physical memory. But the point is with SMM, it can access all of memory, and there's hardware support for locking down SMM so that OS and hypervisors and stuff like that can't access it memory. So you set some code into SMM, you let it run, and then like the BIOS will set and say, lock this code down. No one may ever again, you know, read or write this memory. The only thing that can happen is when you get one of these SMM interrupts, the SMIs, or system management interrupt. When you get an SMI, it vectors into the code, it starts executing whatever you've already put there, and when it's done, it just returns back out to the rest of the OS. So whatever code is already there when it gets locked down can execute as much as it wants and access all of memory, but the OS can't, you know, read or write to that code. So think of it like in the OpenBSD point, the OpenBSD paper, the issue is he got into SMM, and because he was in SMM, he could read and write all physical memory. And if he can read and write all physical memory, he can just, you know, go find the OpenBSD kernel protection stuff, you know, find that memory, flip bits, you know, turn it off, make it so that it's functionally negated. And the same issue will recur with things like virtualization, right? So although you can use hardware-based virtualization to make it so that, you know, my guest OS can't screw with my hypervisor, if the guest OS can break out to it, you know, if the guest OS can get to system management mode, it's now running code which can read and write all physical memory, and that means it can read and write the hypervisor. So there's been exploits where, you know, you're not supposed to be able to get into SMM once the BIOS locks it down, but there's been exploits which have been found which exploit like caching and other just chipset specific problems in order to have the attacker get into SMM, at which point they're more privileged than anything else running on the box. Yes.
So there's also the secure mode that TXT brings in. And I know that a lot of that has to do with nothing else can execute at the same time, but is it also privileged in a way that you can interact with SMM?
Well, first of all, I would say that as I currently understand it, first of all, SMM, I can't remember if this is an implementation vulnerability. The thing I can say is that at like Black Hat Federal 2 or 3 years ago, there was an exploit where Invisible Things Lab was holding on to a private SMM exploit that they had, and they used that to bypass TXT or to break TXT or whatever. And so in that context, it was certainly the case that SMM was more privileged than this, you know, lockdown TXT mode. I can't remember, though, whether that was an issue. There's this issue here of, for instance, in the virtualization case, it is in the spec that there's a way to, like, essentially virtualize the SMM handlers so that it is no longer more privileged than the rest of the system and so that it can't just write all of stuff. But the issue is the virtualization vendors weren't making that. In the case of, or they weren't implementing that, like, let's lock down SMM. Because, you know, it's obscure and most people weren't attacking it. Most people didn't know anything about it. In the case of TXT, I can't remember the details of the attack to know whether it was an implementation thing or whether it was a fundamental thing that TXT wasn't thinking about sanitizing the SMM stuff or locking down the SMM stuff. I feel like, whereas virtualization, it was an implementation thing, people just weren't implementing the thing. I feel like in the TXT case, it was more serious in that it was the case that they didn't have specified at the time a way to lock it down, but I'll have to double check that. I'll go look up that and talk quick at the break. Right, so there's kind of two ways to get into system management mode. One, modify the BIOS, because the BIOS is the one who actually loads up the system management code and says lock it down. Or two, have some exploit type thing, which allows you to read or write things. So there's been like 2 or 3, I can't remember whether it's 2 or 3 sort of actual exploit type things. One was caching one was the chipset one, stuff like that. I think I have links. I don't remember, but they're definitely in like my proposal for research like 2 years ago. Yeah, so the main point is I wanted to mention SMM because it's becoming more popular due to the fact that it's more privileged than other stuff. It's definitely a target for you want to get there, and then you can do whatever you want. You can break up. I mean, if you get into SMM, you have functionally a hypervisor escape vulnerability, right? All right. Yeah, but that's going to mostly go in the advanced class because hopefully we're going to be learning a bunch of stuff about this and TXT and stuff like that, right? The point was let's learn some stuff about this so that we can present the stuff more widely in the future. I like this picture because it reminds me of like a tripod from the Invasion of the Tripods, or if you remember Batteries Not Included movie from the 80s with the floaty little aliens that are just big heads like this. It looks like that too. So this is great. This is from the AMD manual, actually. I had one person who gave a talk at ShmooCon a couple of years ago. I think it was the year before this last one. He had this in here. I never look at the AMD things. I don't believe an equivalent to this exists in the Intel documentation, but it's a great picture because it says, when you get a reset, all roads lead to real mode. Right? So this is the state machine. Oh, and hey, Jessica, this is a great state machine example you could use for your FPGA class as well. When you get a reset, all roads lead to real mode. You restart the processor, you're in real mode. If you want to get from real mode to protected mode, there's this CR0, it's control register 0. There's a PE flag for protected mode enable. You set protected mode enable to 1, and bam, you've now moved into protected mode, and you can use whatever capabilities exist there. And then there was this eflags.vm thing. We didn't talk about it, but we said that's the virtual flag, or whatever it was, virtual mode flag. And so that is what kicks you over to that virtual 8086 mode, right, for backwards compatibility. Also, from protected mode, you can enable this, LME, CR4, blah, blah, blah. You set some bits, and you get into long mode, which is 64-bit mode. So this protected mode is 32-bit, and long mode is 64-bit mode, but there's also a compatibility mode here. So virtual 8086 is sort of like compatibility with real mode, and this compatibility mode is sort of compatibility with 32-bit. But overall, this is supposed to be a 64-bit execution environment. This is 32, that's 16, that's 16. But we've got this little system management mode off here to the side, collected and ignored until it became popular. If you get one of these SMIs, system management interrupts, those, bam, vector you from wherever. Anywhere you get an SMI, you're overrunning in system management mode, and the only way to get in and out is system management interrupt or resume, whatever that is. RSM instruction is how they return out of system management mode to whoever was running at the time that the interrupt occurred. So that's a nice little state machine. All right, any questions on the modes quick on the phone or anything? All right, so I said we're going towards understanding where privilege rings come from and what it means to be in ring 0 versus ring 3. So for historic sake, Multics was the first OS that actually supported hardware-enforced privilege rings. So the key point here is x86 rings are also enforced by hardware. So when we talk about, why can't user space, just read kernel memory and stuff like that, it's enforced by hardware, and we have to see, where those bits are set around in memory that says, like, my code executing right now is ring 0. My code executing right now is ring 3. We've got to find where that is actually stored. All right, and yeah, you probably heard it, but there are 4 privilege rings on x86. The lower the number, the more privileged. So 0 is more privileged than 1, is more privileged than 2, is more privileged than 3. Typically, they only use ring 0 and ring 3. Most OSs never ended up taking advantage of the other rings, and therefore, the 64-bit thing, I believe the other rings actually just got dropped out. So there's still a ring 0 and a ring 3, but they only need 1 bit now to say 0 or 1. So there's user space is ring 3, and kernel space is ring 0. All right, so the key point here is those rings have a lot to do with segmentation, so that's why we're covering segmentation first. But again, here's just a quick picture showing that, here's conceptually what it looks like applications out here at ring 3. Turns out no one ever ended up using 1 or 2. I mean, some high security things did, but no one that had mass market is using them right now. So on 64-bit, I'm pretty sure anyway. But here is one example of how one could potentially leverage those extra rings. So Zen in paravirtualization mode. So paravirtualization is something that was made popular by Zen, and it refers to when, instead of trying to just transparently use the OS as is, for performance and security reasons, you potentially want to make it so that the OS is hypervisor aware, so that instead of the OS going to reach out and try to touch the hardware directly, as it's used to all the time, instead it gets an API to access the hypervisor, and only the hypervisor is allowed to access the hardware because it's managing the hardware for many different OSs that it's virtualizing, so you don't want them stomping all over each other. Like if every OS can directly control, the one control register 0, they're going to be stomping all over each other. So Zen should be the only thing in paravirtualized mode that can access the hardware. The guest OSs are modified so that they're Zen aware, and then the guest OS is deprivileged so that it runs in ring 2 rather than ring 0. And so if it tries to execute some ring 0 instruction that can only be executed from ring 0, it'll cause, a trap or a fault or interrupt or whatever, and the hardware is going to kick it up to ring 0, which is Zen, and Zen will handle it. Yes.
This may be a premature question, but what's actually the difference between level 1 and level 2 in terms of privilege?
I don't believe, well, other than the fact that if you had some code running in level 1 and if you had some code running in level 2, 2 would be more privileged. But in terms of between them versus 0 or 3, well, functionally I would say how it works is there are some places in the system where only ring 0 can do something. There are other places in the system where 0, 1, or 2 can do something. So 0, 1, and 2 are still considered supervisor level thing when we get to virtual memory. And so 3 is definitely always, the least privileged. But in terms of supervisor, for instance, which is the only place I've ever seen something that's not, strictly ring 0, for supervisor mode, 1, 2, 0, 1, and 2 can all do the same thing. So there's no difference there. So it really wouldn't matter whether they're 1 or 2 in this sense. The only place I can think of where it might matter is when we get to that IO privilege level field in the E flags. That can say like only ring 0, 1, or 2, or 3 can access input output. And so in that case, you could say, look, only ring 2 or 1 can access IO and therefore 2 can't. So you could break up some granularity, but for all intents and purposes, 0, 1, and 2 are most of the time just all privileged. It's just that no one. That's the basic thing. All right, so we have to understand segmentation. So here's a nice complex diagram, which the reality of the situation is not as complex as this, but this is sort of a conceptual thing. So I'll do it on here because it makes it easier on Bill. So the concept of segmentation.
Sorry.
Yes.
Can you possibly request a break real quick?
Oh yeah, you're right. It is time for a break. Thank you. 10-minute break. Back at 40 after.